In this session, we are going to look at worked examples, or we are going to look at some solved problems regarding Poiseuilles formula coming up. We get started with this. A liquid flows steadily through a horizontal pipe of length 3.2 meters if the amount of liquid collected at one end is 6 grams per second. What is the pressure difference between the two ends of the pipe? Let's draw that pipe. So this is the pipe we are talking about. This pipe has a horizontal length, so the length of this pipe is 3.2 meters. And at one end, let's say there is this end and there is that end. At this end there is a pressure, and that end also there is a pressure. The question is asking us to find what is the pressure difference between the two ends of the pipe. What is P2 minus P1 equal to? And then after finding what P2 minus P1 is, then hence calculate the pressure gradient. Pressure gradient is P2 minus P1, divide that by the length, which happens to be 3.2. So we need to first find this, then after finding that, we find that right there. And of course, the other information is that at what the liquid collected at the end is 6 grams per second. Now 6 grams per second, it's 6 grams, that is mass. So the mass per second, mass over time, that is the 6 grams per second, meaning that the mass flow rate, or the amount of the mass of the water that is flowing every second is 6 grams of water per second. So this is the mass flow rate. So of course we're supposed to be using Poiseuilles formula to find this. Then eventually we find that. So now where do we start from? Let's first quote this formula. Poiseuilles formula says that V over T, which is volume flow rate, or the amount of volume of water flowing per second, is given by pi r to the power of 4 times the pressure difference, which is this, P2 minus P1, divide that by 8 times the coefficient of viscosity times the length of the pipe. Now we derived this in our previous session, and now we're just going to use it. So now the question is, we need to make this the subject of the formula, the pressure difference, because it's what we need to find first according to the question. So making P the subject of the formula is going to give us P being equal to 8 times coefficient of viscosity times the length times the volume flow rate, V over T, divide that by pi r to the power 4, times pi times r to the power 4. Now that we have made P the subject of the formula, which is the pressure difference in this case, so now we need to go ahead and find it, because the question requires us to do so. But now if you to look at this question, if you look for us to get the P, the pressure difference, according to what the question is telling us, that what is the pressure difference, you realize, yes, we have the 8. We have the coefficient of viscosity of this liquid. According to our question, it has been given to us as 0.92 newtons per meter. We have the length of the pipe. The length of the pipe was given to us as 3.2 meters, right there, 3.2. So we have this, we have the length. We need the volume flow rate. Now the volume flow rate is not given anywhere. Of course, we know pi is a constant. We have the radius of the pipe. The radius of the pipe is 7.5 millimeters. We have that. So for us to get the pressure difference, you realize that we are missing the volume flow rate. So we need to first find the volume flow rate so that we are able to have everything, and we just simply substitute here and we're able to get the pressure difference. But now the volume flow rate we do not have, but what we have is the mass flow rate, which is 6 grams per second. So meaning that if we can use this mass flow rate to get the volume flow rate, and we come and put it right there, and then we will be able to find the pressure difference. So now, if we may call it a bit of side work or something, but we need to first find this volume flow rate. And since we have the mass flow rate, we can move from the mass flow rate to move to the volume flow rate. So let's begin by first finding V over T. First of all, we know that density is given by mass over volume. So it means that if we make mass the subject of the formula, it's going to mean that mass is going to be given by density times volume. Now this is mass is equal to density times volume. So mass being equal to density times volume, if you look at our question, what we have is this. We have mass, divide that by time, mass flow rate. So what we do to this is that we divide both sides by time. So we divide this way by time, we divide that way by time. And when we divide m over t, now we have an expression for mass flow rate. And so mass flow rate is going to give us density times v over t. Now v over t is the volume flow rate. Volume, divide that by time. And that is exactly what we're looking for. So it means that mass, divide that by time, is 6 grams per second. Is going to give us the density. Now we're dealing with the density of the fluid. In the question, the density of the fluid is 1.2 times 10 to the power 3. So this is going to be 1.2 times 10 to the power 3 kilograms per meters cubed. Multiply that by the volume flow rate, which is V over T. So when we make V over T the subject of this formula, we end up with volume flow rate giving us 5 times 10 to the power negative 6. So this is the volume flow rate. Now that we've gotten V over T, now we can go ahead and find the pressure difference. So getting back to our expression, to get the pressure difference, this is going to become 8. Multiply 8 by the coefficient of viscosity. Coefficient of viscosity is 0.92 newtons per meter. So it's 0.92 newtons meter. Multiply that by the length. The length of the tube, according to our question, is given as 3.2 meters. So the length of the tube is 3.2 meters. Multiply that by the volume flow rate. We got our volume flow rate as 5 times 10 to the power negative 6. So that is 5 times 10 to the power negative 6. Divide all that by pi, which so happens to be 3.14. Multiply that by the radius of the tube. Now the radius of the tube is 7.5 millimeters. Now 7.5 millimeters, we convert this to meters so that it's in the right standard units. Converting 7.5 millimeters to meters is going to be 7.5. Multiply that by 10 to the power negative 3. And this is to the power 4. So upon computing all that, our pressure difference is going to be given by, it's 11,846.849 pascals. That's our pressure difference. So we've answered the first part of the question. The first part of the question required us to find the pressure difference between the two ends of the pipe, which we have just discovered. So we go ahead and calculate the pressure gradient. Therefore, after getting the pressure difference, so we go ahead and find the pressure gradient. So in this case, the pressure gradient is going to be the pressure difference divided that by the length of the tube, which is going to be 11,846.849 pascals. Divide that by 3.2 meters. And we shall end up with 3.7 times 10 to the power 3 as our pressure gradient. An empty vessel which is open at the top has a horizontal capillary tube of 20 centimeters and internal radius of 1 millimeter. So we have an empty vessel right there. The question says that it is having a horizontal tube. It is open at the top right here, and it has a horizontal capillary tube. The horizontal capillary tube here has a certain length of 20 centimeters. Of course, 20 centimeters, we convert that, it's going to become 0.2 meters. And internal radius of 1 millimeter. So this is the length of the tube. So the radius of the tube is 1 millimeter. Of course, 1 millimeter, we convert that to meters as well. And that was going to give us 1 times 10 to the power negative 3 meters. Internal radius of 1 millimeter. It is protruding from one of the side walls immediately above the base. That's what I've just drawn. Water flows into the vessel at a constant rate of 1.5 centimeters cubed per second. So this is centimeters cubed per second. Centimeters cubed is volume per second. So it means that the volume flow rate, let's call it V over T, is 1.5 centimeters cubed per second. Now let's convert this centimeters cubed to this SI units. These centimeters cubed, we convert them to meters cubed per second. So it means that our volume flow rate is instead going to be, that will be 1.5, divide that by, and this we will have converted this to meters cubed per second. Now the question continues to say that water flows into the vessel at that constant rate, and now they are asking us at what depth does the water level stop rising? Assume steady flow. Of course, when we are talking about steady flow, we are talking about Poiseuilles formula, and this is the height of when water is coming in. It's flowing in at that rate. So water is flowing into this thing at that rate, and as it's flowing in, it is protruding out of here. So definitely this is a very small capillary tube, and so it means that as water is flowing in at this rate, part of that water is flowing out of this capillary tube as it goes out. This question is asking that at what depth does the water level stop rising? Now, at what depth that the water level stop rising, meaning assuming steady flow, it means that if this height is to be constant and it is not rising, the water levels are rising, that would logically mean that the amount of water coming in is the same amount of water going out. In other words, the rate at which water is coming in, the volume flow rate in coming in here, is the same volume flow rate going out. So definitely, if the water is if this height is to be constant, that is, if this height is to be constant, it would mean that if we are having 1.5 centimeters cubed of water coming in, it would mean that we are still having 1.5 centimeters cubed of water going out, meaning what is coming in is what is going out, and so this height is constant. So if we are going to use Poiseuilles formula, it means that as far as the pressure difference is concerned, we are looking for the height when this thing is the constant height when it's the same water coming in and same water going out. So how do we go about this? First, we quote Poiseuilles formula and we go ahead and find that height difference. So we know that Poiseuilles formula V over T is given by pi r to the power 4 times the pressure difference, divide that by 8 times the coefficient of viscosity times the length of the pipe. So this is going to be pi. As we continue, pi, this is V over T, is giving us pi times the radius of the pipe, which is r to the power 4. Multiply that by, now P here represents the pressure difference. So it means that the pressure difference, this height of water, this pressure of water, we convert that to, it's supposed to be height of that times the density of the water times gravity. Divide that by 8 times the coefficient of viscosity times L. Now in this case, we are interested in the height. We are interested in the height that is going to make this constant, that when the volume flow rate is such that it's 1.5 centimeters cubed are the ones that are coming in here. What is the volume flow rate? What is the height that is going to correspond to that volume flow rate? In other words, when this height is constant, if this height is to be constant and water flowing in is the same water flowing out, what volume flow? Battery, no space. So the pressure difference here, which is maybe the pressure at this level minus the pressure at that level. The pressure difference is given by height times density times gravity. So the height of the liquid column that is going to be produce that pressure is converted into this. And now we go ahead and find the height. What is that constant height that is going to enable this volume flow rate to be constant all through? So we make h the subject of this formula in this case, since we are looking for the height. So h to make h the subject of the formula is going to become 8 times this the coefficient of viscosity times the length of the pipe, multiply that by the volume flow rate, divide all that by pi times r to the power 4, multiply that by the density of the water, multiply that by gravity. So now that we have made h the subject of the formula, we go ahead and substitute in the rest and we get the value of h. So this is going to become 8, multiply that by the coefficient of viscosity. Now according to our question, the coefficient of viscosity is 1.0 times 10 to the power negative 3, so it's going to be times 1.0 times 10 to the power negative 3. Multiply that by the length of the tube. The length of the tube, according to our question, the length of the tube is 0.2 meters right there. So this is going to be times L, which is times 0.2. Multiply that by the volume flow rate. Now we got the volume flow rate, we converted it to meters cubed, according to our question here. So it's 1.5 over that. So in other words, it's 1.5. Multiply that by 10 to the power negative 6. The volume flow rate, divide that by the pi, which is 3.14 times the radius to the power 4. Now our radius was converted to meters, which is 1, times 10 to the power negative 3, and this is to the power 4. Multiply that by the density of water. Of course, the density of water is 1000 kilograms per meters cubed. Multiply that by gravity, which is multiply that by 9.81. And so the answer we end up with here as our value of h, or as our height, is 7.8 times 10 to the power negative 2 meters.
This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.